Hello, my name is Milton Dennis Earl, and I'm a retired high school physics teacher. I've developed a model of the universe, an exponential model of the universe, that should interest cosmologists everywhere. The standard model that you know is refuted by this model, and it involves exponential mathematics, which is quite different than the standard model. And you may say that, well, relativity has been proven many times over. However, I think I can convince you that, in fact, relativity is only an approximation of the true nature of things. The standard model has been having problems recently, and more people have been questioning its validity, especially since you have something like 95% of the matter and energy in the universe as being referred to as dark matter and dark energy. These videos will explain my model. It is a mathematical model, but it's not the mathematics associated with relativity, and you'll see why. I go back as to the very beginnings of the logic behind relativity and question that. It's easy to criticize a model. The standard model is questioned now because of the results of recent technology improvements. But questioning it and criticizing it is easy. It's the ability to provide a viable alternative to the standard model, and I think I've proven this here. Now, I know there are many crackpots. I hope you don't think I'm a crackpot, but I've been a staunch soldier for many years now. I was first introduced to relativity at the college level in the early 60s. This model, as I said, is mathematical, but it is not the linear model that you are familiar with. Instead, it is an exponential mathematics that you must apply to the universe, and it's derived from Hubble's law. Now, Hubble's law, if you do the integration necessary and use the logic behind it, you will see that it's quite a difference between that and what we do today. And I know that the term circular logic is a very annoying term to cosmologists today, but there is a certain amount of circular logic that is used to prove the theory as it exists. You cannot describe an exponential universe with simple linear mathematics, and that's essentially what Einstein and others early cosmologists did. How far back do you go? If you have a theory that doesn't work, it's sort of like having a math problem that doesn't work at the end. What do? You go back in time, you go back on your paper and you go, okay, this is correct, and you just keep going back. Well, the scientists today think they're thinking outside of the box, but are still accepting relativity as it stands. Now, what I did was, and I was doing it with a tremendously open mind, I was saying, okay, the early cosmologists had no idea that the Milky Way was anything but the entire universe. It took Hubble and a couple, the Hale and Palomar telescopes to show that, in fact, it wasn't the only thing going. There were countless galaxies, just like our galaxy, the Milky Way, and that they not only existed, but they were moving relative to us. The farther away, the faster. I know I'm going over things you probably know. These cosmologists, the people who derived relativity, including, of course, Albert Einstein, there's Lamont, there are a few, Friedman. These people did not know, they did not have access to that knowledge that we have today. We have a lot more information than they did, and we're not using the information that we have to adjust our reasoning. The most recent technology I will bring up too. It's the New Horizon information that was received in 2015, which lends a lot of credibility to my theory. Really quickly, there were two postulates that actually were the basis for relativity. One postulate was that the speed of light is a constant throughout the universe. That's reasonable because people like Michelson and Morley showed that no matter what direction you're moving, no matter how fast you're moving, you will always receive light or transmit light at 3 times 10 to the 8th, roughly, meters per second. So therefore, C is a constant. The second postulate that's as a basis for relativity is that the laws of nature are the same. The physical principles are the same everywhere in the universe. And since we on Earth experience gravitation, gravity is part of the whole deal. It is universal. Now, these two postulates are under fire in my theory because they started with Hubble's law. And I said, that seems to be a more natural law. Now, if you look at the two situations, gravitation is what we interpret as a pull. If you look at the universe as a whole, the galaxies are expanding and going faster and faster as you get greater distances. So instead of accepting gravity and accepting everything in early physics, and when I say early physics, I'm talking about Newton and Einstein and the early 20th century, the innovations in mathematics and science in the early 20th century. Forget all that. I said, let me start with Hubble's law, and you'll see that you can derive Hubble. You get out of Hubble's law, you get an expression for distance, you could say, or velocity, that is exponential in the universe, and it's a growth equation. So I will show you that actually in the first video. The speed of light in my model, as it turns out, after I do all the mathematics, is that the speed of light is moving at the speed of light relative to us all the time. It's kind of interesting that I would put it that way, but you'll see the math behind it, and actually no matter what direction you go, you will measure the speed of light as being 3 times 10 to the 8th meters per second. However, it is not moving that speed everywhere in the universe. So if you're located on a distant galaxy, it's moving much faster than it is where we are, etc. It's expanding along with the universe itself. The second, now there's a fine difference there. You cannot count the speed of light as being constant. Now, Lorentz did his transformation, famous Lorentz factor, based on the fact that the speed of light was constant, and he did all his calculations. Well, if you're going to do that, you have to make time a variable, and that's where we get time dilation, we get mass increase at high speeds, and length contraction in direction of motion. These things all are principles of special relativity, and they exist because c is a constant, and it goes right back to Lorentz, and Lorentz was used in Einstein's calculation. So that's the first thing. Speed of light is not constant in the universe. It expands with the universe. The second thing, the second postulate is that the laws of nature are the same everywhere, the laws of physics. Well, that's true. The only thing is, we can't say gravity is the same exists everywhere in the universe, like say the universe as a whole, for instance. That's absolutely easy to understand because the universe as a whole is expanding. So what I did is I came out with a general equation for the expansion of the universe, the exponential volumetric expansion of the universe caused by the matter distribution. And you see, on Earth, we are on a concentrated piece of matter. When you use the numbers on a concentrated piece of matter, such as a star, a moon, a planet, when the concentrated matter is considered under my theory, you will see that it produces Newton's law. And that's probably the simplest part of this. That's part of what got me going on this thing. I started with Hubble's law, and I developed the fact that the general equation for the universe explains all phenomena that I know of. I haven't delved into certain things like the CBR. I haven't done that yet. I'm confident that it's going to be a simple thing, not a simple thing, but a valid principle. Now, I'd like you to look at this. I used videos because I learn a lot better from a video, and you can see it's essentially a lecture, and it's boring for those of you that don't know mathematics. But I maintain that this theory can be understood by a good high school physics student, and that it is a lot easier to accept than the standard model. So give this a go. This is the introduction that I'm using now. I will get by the whiteboard and show you what I mean. Well, the first thing I would like to do is talk to you about how I derived this theory. It's the theory of infinitesimal, continuous, exponential expansion of all things. It's matter-induced. It's an expansion of not only matter, but matter and space. If you stick to very simple principles, you will come out with some amazing results. Now, I want to just say that how this thing started was I was in class one day, and everybody knows G m1 m2 over r squared negative force equals, that's Newton's law. Newton said that if you have two objects, m1 and m2, with a distance between them r, that a force will be exerted by one on the other, each one in this regard. Now, as far as acceleration, since F equals ma, acceleration is just simply g, and we'll call this Newton's g, m over r squared, for some body in the middle of nowhere, and it will cause an acceleration on some other body in this manner, and you'll notice that it's meters mass per square distance. And if you look at this Gn is Newton's G, and it's a very small number. It's about 6.7 times 10 to the minus 11th meters cubed per kilogram second squared. Now, for this theory, for this model of my universe here, I will be using System International units, which is kilograms, meters, seconds. I don't understand why anybody would change that and try to get a general picture of everything, but this is the usual way you do it. I do this SEC because if I use S, sometimes it gets confused with 5. So what I do is I write seconds. I do a few things like that. Oh, I'll use a large R. This R here is a variable, but I do it because it's easier to write, and I think a small r tends to be difficult to imagine. I mean, difficult to differentiate between that and I don't mean differentiation. It's a different. It looks like other figures. Very simple thing. So I'm just saying that this calculation here, you'll notice I drew spheres. For the most part, it's spherically symmetric. The calculations, simple as possible. This G here, by the way, is Newton's G. He's given credit for it. However, he never came out with the value. This was Cavendish and others that did this and came out with this very small value. That's why we're not coagulating. You don't feel the pull of gravity from somebody standing next to you because your m's are very small, but especially because the coefficient here is a very tiny thing and you don't really notice that. Well, if I take that G and I look at it, this Newton's G is in units of, not equal to, meters cubed per kilogram second squared. And one day I was doing some calculations on the board and I looked at this and I said, wait a second, this is meters cubed per second squared per kilogram. And it just seemed very strange to me it would have those units because this, you see, is an acceleration. It's an acceleration of a volume, cubic meters per second per second. Here is a statement that says per kilogram there is an acceleration. That's the unit, that's the constant here. Every kilogram gives this acceleration. Well, it's kind of saying that there is some expansion of a sphere. It doesn't necessarily have to be a sphere either, but it is an expansion of the volume caused by the mass. Well, if that's the case, somehow gravitation might be related to an expansion. So I let it go for a couple of years. I retired. I like to do mathematical projects as a matter of enjoyment. And what I did is I said, if G is a volumetric expansion, how can I, an acceleration, how can I express that as simply as possible? What if I say there's a volumetric acceleration that's equal to, as simple as possible, some constant times the amount of matter present. Okay? Some constant times the amount of matter present. Well, keeping it simple, this constant is one thing, and I'm going to call that, since I think it's related to G Newtonian, I'm going to call it the constant G sub E. That was a guess. Okay, and this here times matter. Well, how can I keep that as simple as possible? Let's suppose we say it's a matter that's not varying, constant. So my expansion constant here times m0 is the acceleration of the volume. That means that here's a sphere. As time goes on, the sphere gets bigger and bigger and bigger. Okay? Now, that's the acceleration of the volume. But what does this field here, this acceleration field, look like, and what's it do between here and the center of mass? Well, if it's an expanding sphere, then it's got an expanding velocity. And that I'll put down V sub V. Volumetric velocity. How fast is the sphere getting bigger as far as the volume goes? Okay? And that would be just the integral of this. Well, the integral of that is from your constant acceleration equations from physics. The integral is very simple. This is a time integral. What you do is you just say it's equal to G sub E m0, and of course the integral of 1 is t. If I differentiate this, the t drops out and it becomes your acceleration. Well, that's your volumetric velocity. And if we take it one step further, if I take the integral of the velocity in terms of constant acceleration equations, becomes at squared. So what do you end up with? You end up with a volume of 1/2 G sub B m0 t squared. If you check out the dimensions here, times squared, meters squared, meters cubed per kilogram, seconds squared, cancels out, kilograms cancel out, you come out with a volume. The volume now is equal to this, but there is one other volume that we can mention. Any volume, the identity for any volume is 4/3 pi r cubed. Okay, you see that from geometry. And then if I take the differential, if we differentiate this, we get a volumetric velocity of 4 pi r squared dr dt. Now these two things here are equal. These two things here are equal. Well, one thing, well, I'll bring it up later, but it's kind of Kepler's law here. But I didn't notice that at first, so I'm not going to mention it right now when I was doing it. But what I did was I said, therefore, let's look at the volumetric velocities and call them equal to each other. G sub B, m0 t equals 4 pi r squared dr dt. That is an equation arrived at from just assuming a constant volumetric acceleration. This equation here. Now, if I look at this, I can get this right here is very good. Dr dt is equal to something. Well, that's the change of the, it's the rate of change of the radius. It's the velocity of the radius. How fast is that thing increasing? That's dr dt. And you see, if I solve that, it's equal to GE m0 t
over 4 pi r squared. All simple math thus far. Well, what does that mean? I don't have any idea because r is a function of t. I've got r is a function of t here. And I got a t. So what I could do is go down to these the identities here, solve this for t, plug it in there. It's a little bit of math. It's a little bit of a chore. But what you end up with, which is just incredible, well, we'll see. We end up with the volumetric velocity, dr dt. I said volumetric, I meant the radial velocity, is equal to v sub r, radial velocity, and that is going to be the square root of GE m0 over 6 pi r, all enclosed within the square root. Well, what does that mean? It looks familiar, but it's not that familiar. What I can do after this is I could say, well, what's the second derivative of r with respect, second time derivative of r? The second time derivative is this, the second r dt squared. It's equal to your radial acceleration. Well, if I differentiate this, this is the first differential. The second one, it comes out to be G E m0 over r squared times 12 pi, and it's negative. Now, you can do that. It's very simple. Once you differentiate, this is r to the minus 1/2, and then minus 1/2, you end up with that, and then you just take this, it ends up with dr dt, and when you multiply it out, the square root sign disappears. Well, what does this mean? If I look at this, I've got a negative value for the radial acceleration. I've got some constant times the mass inversely proportional to the radius. That's Newton's law, where my GE is equal to 12 pi times Newton's GE. Okay? So this GE here is larger than Newton's by 12 pi. If I substitute 12 pi GN in this, 12 pi's cancel out, and I end up exactly with Newton's law. Now remember, Newton's law is on the Earth. This was derived on the Earth, I should say, but it was used when he did it. He did the calculations with the moon and everything, and it's kind of accepted that it's everywhere in the universe now. That was an incorrect assumption. The assumption that Newton's law pertains to every mass in the universe is incorrect, and I found that out after I went into Hubble's law. But this right here says that GN is related to GE, and if I do that, I put that in here, I get, this becomes 2 GN m0 over r, square root of that. That's the escape velocity for Newton's law, for gravitation. I thought that was fantastic. I thought it was fantastic that I got Newton's law from just making an assumption that a volume with a certain constant mass in it became Newton's law when you're taking radial values. And radial values are the ones we think of. We think of how fast something's going, in what direction, etc. We kind of got a feel for that. This volumetric stuff is a little more hard to figure out or imagine in your brain. Now, what I got from this was this, and I said, that's just fantastic, and I tried to contact people. Have you ever seen it? No one's ever seen it, but it was deemed a coincidence. Pretty much of a coincidence, but it's a coincidence. Nobody wanted to accept a paper that I wrote on it, etc. I just found it just fascinating that this AV, being a constant, generates an acceleration which is radial, and it's Newton's law. So what I want to do now is start with Hubble. What I want to do first, though, is go back a little bit, and if you recall, 1/2 G sub E mt squared is equal to the volume from integrating from the constant acceleration equation, and that is equal to 4/3 pi r cubed, which is the definition of a volume. One thing I mentioned in passing, but it's another piece of evidence for there being some relationship between an expansion and gravity. And this is it. R cubed and t squared are the only two non-constants here. And you see r cubed over t squared is equal to the constant. This is one of Kepler's discoveries, one of his statements. He had 3 laws, I can't remember what they were, but equal areas, equal time, etc. This is a Kepler's law. So it kind of agrees with the work that I just did on the board. Now, this is all circumstantial evidence, and is it great shakes? I don't know. Maybe somebody's done it before, but I doubt it. And it really led me to continue on, even though the response to that was nothing. The response to a volumetric acceleration, which is constant, leads to Newton's law. Well, I want to just go over Hubble's law here. Edwin Hubble and Palomar and Mount Wilson did some work. There were others before him, but he is given the credit for coming out with some very important things in the universe. One of which is that the nebulae, the clouds that they thought they saw through telescopes, they thought they were dust clouds in our Milky Way galaxy. He showed, using standard candles for Cepheid variables, he showed that in fact they were separate island universes located quite a distance away. So he's given credit for discovering that, and the second thing he's given credit for is finding out or determining that there's a relationship between how far a galaxy is from our galaxy, and we're talking about galaxies here, hundreds of millions of stars. There's a relationship that seems to be true at that time seemed to be true for the entire universe, was that if you had some galaxies here, and this one, and this one, I'm drawing these arrows, hopefully bigger, and you have an observer here looking through some huge telescope. If this observer looks, he sees galaxies that are closer. This galaxy are moving at a slower speed away from us, and that is in all directions, symmetry in all directions, they're moving away from us in an they're moving faster if they get farther away. I don't know where I started that sentence, but basically he discovered that the velocity of these things is equal to some constant times the distance. Well, mathematically speaking, it's a very simple thing to do, and since I'm keeping with the r thing, the distance is r, and the constant, I think we'll name it Hubble's constant. Hubble is the one I think that started it, but that's his HO, and you know the radial velocity, which we talked about already, dt. And what this says is that this is the speed of the galaxy. This is the distance. As the distance increases, the velocity increases. Observable. Okay? Now, how do they observe these things? They observe them with standard candles. How big of a light bulb, how much light would be received by us if the light were a mile away or 10 miles away? You get less light. It's inverse square. The other way is through shift, wavelength or frequency shift, Doppler. We address that, but the Doppler shift also tells that. But what Hubble came out with was, this is Hubble's law here. dr dt is equal to HO. Now I'm going to do the math very quickly here. 1 over r dr equals HO dt. If I take the integral of that, I come out with, and we're going to use the standard computation for integrals here, HOT, that's easy to do, is equal to the log of r plus a constant. Well, convention says you make it minus the log of r0, some initial r. Okay, that's math. I don't know, you'd have to look it up. But the log, this indicates that the log of r over the log of r0 equals HOT, which means e to the HOT, taking the natural, I'm going to give you the rule here, e to the e to the log of a equals a. So this is e to the log of r over r0. This is equal to r over r0. Kind of quick, but you see here that r is equal to r0, some initial radius, some distance, times e to the HOT. This equation here is called a simple growth equation. It's used for computing interest by economists. It's a common thing, and they use S for the amount of material is dependent upon, the new material is dependent upon the original material. This here, apparently the distance the thing is dependent upon the original distance. Now, what does that mean? That means that every one of these things, according to him, every one of these things are going through an exponential movement, exponential expansion. The universe is getting bigger by an exponential amount. Now, granted, this HO, he computed it to be, I forget what he did, but it apparently is about 10 to the minus 18th. I'm putting that down. They have a variety of things. They're getting closer, I think. I'm not really sure. 10 to the 19th, and this is per second. The units are per second. And you see it would be per second because HO times the time would give you a number there, e to some number. Now, some things and we'll go over this a little bit later, but what if the time is 0? If the time's 0, it's e to the 0. You don't have a 0 in this expression. E to the 0th is 1. So it doesn't go away. What does that mean? If you look at this, at time 0, R is equal to R0. Kind of makes sense. So what we have here is this statement from Hubble's law. Here's Hubble's law, and Hubble was saying in this statement that the universe is undergoing an exponential expansion. Well, that was fine with everybody, but they started testing. They started looking at it. And I'm going to try not to erase something important, but I'm going to just show you what happened with Hubble's law. There are a couple things. First off, here is the distance. Here is the velocity. Radial velocity, we'll call it, right? If Hubble's law is correct, I erased that. If Hubble's law is correct, this line could be HO, and HO is a constant. We're calling HO a constant, by the way. We start out simple, then we can worry about the early universe and all that stuff. But we're calling it a constant now and before. HO is the slope of this curve, where R and VR are proportional, and the slope of the curve, these galaxies should be on this. In other words, the farther away it is, the faster it's moving. Okay? And that HO is represented by that curve. Okay, so it worked pretty well for Hubble and others, with their early telescopes. And I say early, 20th century is pretty good. Really early is Galileo, but these things work pretty well. But we noticed some. The further they went out, the less accurate it was. And you had these outlying. I'm just drawing this offhand. You can look it up. You can do it on the internet. Approximately, these things are out away from the curve. So that was a problem. The problem was that Hubble's law was true for closer galaxies. You do realize, of course, a close galaxy is light years away, many light years away. So as you get further out, the more they did, the more they found discrepancies between Hubble's law, this dr dt equals HOR. There was a discrepancy. You see, dr dt divided by R is HO. That's this. Somebody came out with was that Hubble's law doesn't quite cut it, and actually it became a parameter where it has changed over time. I'm trying to keep this theory, when I'm doing this, I'm trying to keep this theory as simple as possible. And what I decided to do was say, okay, there's no visible evidence that Hubble's law, his constant, HO, has changed. Everything about this changing value of Hubble's constant is mathematically predicted by the standard model. There is no evidence that it has to be variable. And that's why I also have a problem with a changing Hubble's constant. Well, what's this say? It means that these things are all moving at this, and I'm going to keep Hubble's constant as being gospel. This is gospel. If I do that, I can take a look at the universe And don't worry about these measurements for now. But you will see, when I do this, you will see that these little dots here are wrong. The method by which astronomers do the math, the math. They use relativistic Doppler shift. It's wrong, and I'm prepared to prove it mathematically. But because these are wrong, now you got things going on like an early universe with inflation and all that stuff. By the way, this exponential expansion is not inflation. Inflation was put in by cosmologists to explain the early universe and have it agree with the standard model. I did say, wrongly so, that log of r over log of r0 was equal to r over r0. I believe, I don't know, e to the log of r over r0 is not correct. It should have been this in there, and that's equal to r over r0. I said it correctly, I wrote it wrong. So the general rule is, and I went over that, log of a, e to the log of a is equal to a. Same idea, okay? So that's a correction, a mathematical correction, that's fine. I want to go over the cosmic expansion equation, how I got that. And the way it goes basically is that the distance r is equal to r0 e to the h0 and t. Now, if it's a position where TA is located, we would call this RA, or any subscripts. But the idea is that the distance to a galaxy is increasing all the time. Now, why could that be possible? I wasn't worried about it at the time, but to me, the whole idea here is that if I have two different triangular galaxies, if this one expands and this one expands, would not be able to recognize a difference in the size, especially if the space in between goes from this distance to another distance. What would I see if I were standing here? I would be bigger here, and this is actually what I'm predicting here. I would be bigger, I would see everything the same in these two cases. Now that's essentially what I'm saying. The exponential expansion is so small that we do not notice it except for certain things like light traveling through the cosmos. Gravity is one embodiment of the expansion, but this is the statement that Hubble made. Now, that means that each one of these galaxies that are traversing the universe, they are, from an observer, they are moving faster the further away they are, because the time differential between the two, which turns out to be all important, dr dt is equal to the radial velocity, and that is the the differential of this. If I differentiate this expression, now how do you differentiate exponents? Well, if it's a e to the a t, where a is a constant, it's simple. If this HO is not constant, then we got a little problem. But like I said before, I'm trying to keep it simple. Keep it simple, stupid. It's the KISS method. Keep it simple. I'm keeping it simple to see whether or not anything happens. And a lot happens. Keep HO simple. And what we have here is, if you differentiate this with respect to time, I got AT there, that's equal to, that's constant. The differential of this is the same expression, exponential expression, but multiplied by the constant that's in the exponent. Well, that makes this nice and easy. Over here, the velocity is the, when you differentiate with respect to time, this expression, that's HO R0 E to the HOT. Very simple. Now, this is a factor here, coefficient HOR0, that is very important. And I'll tell you right now, from a lot of consideration that I gave it and everything, I'm going to write a few things down here. H0, R0, and these don't violate any rules, is equal to, I came out with a assumption that the expansion is maximized. Well, how do you maximize it, the expansion? You say it goes as fast as it can. Well, I'm saying HOR0 is therefore equal to C0. Okay. Now, another relationship, after you think about all these things, first off, HO is equal to the reciprocal of T0, which is the age of the universe. Now, how do I get that? Well, I'll just say this. C0 times T0 is equal to the radius of the universe. That's another expression. Velocity of light times the age of the universe is the radius of the universe. HO is the inverse of T0, and you see what HO is in per seconds. So if HO is 10 to the minus 18th per second, then T0, this is just incorrect mathematically, but T0 is about 10 to the 18th seconds. And that should be about 10 billion years. Now, in this model that I'm proposing here, the distance to the edge of the universe is located at T0. That's the edge of the visible universe, the outside dimension. The dimension of the universe is dictated by T0. Since everything's expanding, it's not changing. It's still T0. I'm going to do some calculations when we get into the Hubble flow that'll show you that the time differential, the light time differential between galaxies does not change. And since this is light moving, etc., T0 just defines where the boundaries for the universe are from a particular observer. Okay, so I'm just going to go back to this again. What's the velocity, radial velocity? It's the speed of light times e to the HOT. I guessed that, but it turns out to be correct, and Hubble and everybody else goes with that. I'm using C0 as a constant, but in reality, if you look at this, what I'm saying is that these galaxies are moving at the speed of light. Why don't we see them moving away from us? Because we're moving at close to the speed of light, and what this velocity that we measure is going to be the relative velocity of the galaxies. It doesn't matter if, imagine you're in a car, middle of the night, you look at taillights up ahead, you could be going 80, and if those are going 85, you're seeing a 5 mile per hour movement if you don't see anything else. It's a relative velocity. And these things are not relatively moving
at the speed of light. They're moving at some measured velocity that we measure here. But the idea is that they are, with respect to a static universe, a stationary universe, they're moving at this velocity. I'll go into the equations for the velocity, the relative velocity, a little later. If this is the velocity of the galaxy in question, then how is it moving? How is the velocity changing per time? Well, the velocity changing per time is the second derivative of r, and we call that the radial acceleration, and that was, you know, it's in terms of gravity, the radial acceleration is inverse square law negative. Here, you'll notice what happens is we give this a little square sign, and it's a very simple differentiation, E H O T. This is the radial acceleration of a proper galaxy. Now, what is a proper galaxy? A proper galaxy is one which obeys Hubble's law. Okay? Now this R here is R0 e to the HOT. This is what Hubble wrote. He didn't know they were exponentially going, and this essentially says it. Now, the you'll notice that what's this maximized at? The RDT is, this is light, R0, HO square R0. Now, if you do this, you look at this, and you see that this is actually HO times the radial velocity, which is equal to HO, and like I said, we're going to call this C0, C0 e to the H0t. Now, in this model, C0 e to the HOT says this, that light is not moving at the same speed everywhere in the universe. That is a misconception. Instead, what this model says is light moves faster as it is farther from you. But if you were to be at that location and you measured it, you are accelerating at the same rate, you would measure that as constant. It would be 3 times C0 is about 2.8, you know, 3 times 10 to the 8 meters per second. And once again, I'm using the SI system. We used to call it the MKS system, meters kilogram second system. They went to SI, I don't care. Meters per second, that's the speed of light. In a vacuum on the surface of the Earth, in space. Okay, these values here, for instance, if you look at this, it's about 10 to the 18th. This is about 3 times 10 to the 8th. This is the radius of the universe according to this model, and the other model too. 3 times is about 10 to the 26th meters. Meters per second times seconds. HO is minus 10 to the minus 18th. T0 is 10 to the 18th. Very consistent here, but you'll notice they're all coefficients. They're not the accelerated, they're not the exponentiated values. Now, this is the radial acceleration. How fast is the speed of that changing?
if we go to the other side of the coin and look at the volumetric, what's going on volume-wise. If you recall, we were talking before that the volume was increasing in a constant acceleration manner. The volume was constantly accelerating in its expansion. Tough to remember all these terms. Okay, but what I could say is this. I know that the volume is equal to, and this is the dynamic volume, this is equal to 4/3 pi r cubed, and that's equal to 4/3 pi r0 cubed, mathematically speaking, e to the 3h0t. This is the volume. And I'm going to simplify it by saying 4/3 r v0, 4/3 pi r0 cubed is really v0. So the volume is v0 e to the 3h0t. Now there are two things I want to get to here in these calculations. First off, I want a better explanation of HO. The second thing is that I want to get the volumetric acceleration and see what that looked like compared to the constant one we started before, and see what that has to do with anything. And you remember that the constant acceleration came out to be Newton's law inverse, negative inverse squared, and everything. This one we expect will tell us a little something about the cosmic expansion. And what I'm going to do is say that dv dt is the volumetric velocity, and that's equal to this, and that's a constant, right? So it's equal to 3h0 e to the 3h0t. If you look at this, you will see, did I grade everything there? No. V0, there's a V0 in there too. I'm going to put V0 out here. Okay, so what we have here is an expression for the volumetric velocity. And if we go a step further, we will say there's an acceleration. I'm going to go up here to do that. Volumetric acceleration. And you see that the acceleration is changing too. Not only is the volume increasing, but it's increasing its increase. And you know, this is what, I got to say this. There is going to be a volumetric acceleration. We see that the radial acceleration is increasing also. This is what Perlmutter and with the type 1a supernovas, this is what they discovered in the late 90s, that the contrary to popular standard model people, their viewpoint, contrary to a converging universe, a closed universe, what's going on is not only is it expanding, but it's expanding faster and faster, contrary to what they were expecting. And this, by the way, is the reason why we have such a thing as dark energy, because the standard model has to fit it, and if you don't put dark energy down, it doesn't make sense. So there's another problem with the standard model. Well, this says right here, this radial velocity says, radial acceleration says not only is the universe expanding faster and faster as t gets bigger, but you see it is accelerating on top of that. So why? I didn't know what was going on before, and I discovered that it was supposed to accelerate before I knew that Perlmutter and those guys were doing the work. I could have told them that. But, you know, I don't know. I got another thing. AV. Acceleration, the volumetric acceleration in this is the big equation. And what that would be I would differentiate this expression. It's 9. This seems silly, but HO squared V0 E to the 3 HOT. Okay. Now, I went out on a limb here. I had that expression, and I had a lot of other stuff. But I went out on a limb and I said there's a relationship between my work before and the work that I'm doing now. And I said, why don't I just say, I tried several things, by the way, but why don't I just say that, you know, you're talking about the universe here. You're not talking about a mass. You're talking about a density. There is no empirical evidence. That's empirical, not imperial. There is no empirical evidence that the density of the universe is anything but constant. Okay? There's nothing's been experimentally shown that the density of the universe is reduced as you go further out. These are things that come up in the standard model to make the standard model work, and they're mathematical. But experimentally, they haven't shown that the density changes. So I'm going to say that the density is this. It's R0, and it's rho 0, I'm sorry. It's the mass of the universe divided by the volume of the universe. Okay? Okay, and this is this right here. Okay, and I'm going to say that I'm going to go with AV equal to, and I'm going to be consistent with what I had before, and that would be the usual method. Let me write this down and then talk to you about it. This expression here, if you look at the rho 0, V0, that's M0. Okay? GE M0 E to the 3. What I've done is I've taken, and this is a guess once again, I've taken the GEM from my previous constant acceleration equations, and I said, okay, this is GEM right there because the V0 cancels out. You see, if you multiply this by V0, you get M. And I've made it an exponential expansion. I've made it an exponential term. So what I will do then, I will say this and this are equal. And what I'm trying to do here is find out what is my value for HO. And I'll just go 9 HO squared V0 E to the 3 H0T equals GE times the density of the universe times the volume of the universe, and this is the volume here. We're taking it all the way out. E to the 3 H0T. This is the density within the sphere. And if we're talking about the universe, we're talking about the universal sphere. You could call it the visible universe even. And we'll cancel these things out and this thing's out. And you see it's not an exponential term. And if you solve this, HO squared is equal to GE rho 0 over 9. So HO is equal to the square root of GE rho 0 over 3. I took it outside the took it outside the square root sign. This differs from what I was reading about the standard model and drove me crazy. Why is mine different? And I found out that the reason was because of Friedman and a few others making calculations based upon gravitation being a universal phenomenon, and this is much more simple, and it is, I believe, much more correct. It's just the constant times rho zero, which is the density of the universe, divided by 3. And that's my HO. Now, if I take that, oh, where's my A? Okay, if I take that for HO, okay, and put it in this expression, I'm going to erase proper and this and that. I'm going to put the grand total up here. Okay. AV A will turn out to be the volumetric expansion is going to be related to the mass. It's going to be mass generated. It's 9 HO squared, which is G E. This is squared, right? G rho 0. Now I put rho 0 down there. There's more to be said. I'm telling you, this whole thing is so extensive. I had no idea. So I'm just sticking. This is about the simplest stuff. G rho 0 over 3 squared is 9. Where am I? H is 9. Equal times V0 E. Now 3 HOT. So 3 HOT, HO is this. So 3 is the square root of GE rho 0 T. Okay, so AV, and this is the final equation, is equal to GE rho 0 V0. I could just put M0 there. E to the square root of GE rho 0 T. This is the general cosmic expansion. Okay? That. Now what's it mean? It means a lot, actually. Now, what I want to mention here is that Hubble, the Hubble relationship was exponential in form and is. And remember, we're just assuming that H is a constant. There is no empirical evidence that it's anything other than a constant, except that the standard model says it's a constant. It's a constant at this time, but in the past it has varied, and that's just to make it work. Now, what I'm saying here is we're going to consider it a constant all of the time. Now, I mentioned that when you take a Maclaurin expansion of this, you come out with HORT plus your initial starting point, which is R0. We're not going to worry about that starting point right now, because that's something about the Big Bang that I want to discuss after we look at the expansion as it occurs. Now, we're going to be taking distances, positions, etc. But some things we have to get straight first. First off,
yet we have to accept a few assumptions. Now, assumptions are scary because, like I said with the Standard Model, they assumed that Newtonian gravity existed everywhere like it does on Earth. And Newton actually did his work, sitting under the apple tree. In actuality, he was imagining the distance and the fact that the moon was falling toward the Earth. And he did all his calculations based on astronomical objects. And he came out with very good approximations. I mean, that's all they use in the space program now. Newtonian physics, not the only general relativistic things that they do is your satellites. But that too, it has to be scrutinized. But in this case here, we know that the radial velocity of the expansion is, remember the rules, HOR 0 e to the HOT. It's the same function, the expansion, the exponential expansion factor times HOR now. Now, what I'm saying is that here we have a couple galaxies. This one's moving faster. But why don't we say that the galaxies are like falling? They are going as fast as they possibly can. Now, I mentioned it before that there's no way you can tell whether we're moving slowly or fast. We can only see relative velocities here. We see this galaxy is moving X amount of meters per second, but we don't know how we're both moving. And what I'm saying is, suppose we say it's maximized. Well, how do you maximize a velocity? You say that it's moving at the speed of light. Now, in this theory here, we're looking at the cosmic flow. The cosmic flow is increasing as you get further away from us. If light was a constant, and it was this constant distance in a certain amount of time, if light is represented as a constant, you see, it would be as this one gets faster, as the universe gets faster, and if light were constant, we would somehow see the effects of light slowing down. That's not what happens. As a matter of fact, light in this theory and any peculiar motion is that motion which does not obey Hubble's law. Light is peculiar to Hubble's law. It is moving faster than the galaxies are, the relative speeds of the galaxies. So light is a special case of the peculiar motion. Now what I'm saying is, therefore, light is not constant. Light is not constant. In fact, in actuality, relative to the galaxies, it is expanding at e to the HOT. In other words, this would be the speed of light at any place. Here, light, a guy looking at light here would see this. And this is all mathematically, this would be E, if this is TA here, this is TB, light here moves at C0 e to the HOTA. Here it's C0 e to the HOTB. Now, if we look at this, you see, HOR0 is the velocity of these galaxies. And if we make the assumption that the galaxies are moving at a maximum value, this becomes C0 equals H0 R0. There are many factors where we can consider this as being true. I'm going to put some other relationships here that we can assume is correct. And these relationships
Some of them were derived by Hubble himself. For instance, this HO is equal to the inverse of, I'm going to call it capital TO. What is this? This is Hubble's constant. What is this? The age of the universe. Okay? That's time. Hubble's constant is given in per seconds. This is seconds. So therefore, per seconds and per seconds. Well, is that consistent with the top one? If you do the algebra here, C0 times the age of the universe equals R0. Okay, now what is this saying? This is the radius of the universe. Hubble. This is all Hubble. Okay, now, how can we do this when then we already went through the fact that everything's expanding exponentially? Well, take a look at this. T0 is equal to, let me use T0. Okay, T0 is equal to R0 over C0. Okay, now, but the universe is expanding. This takes a little thought on aside. I'm putting these down. You have to really think about these things independently. But T0 is the age of the universe. It's R0 over C0. Well, notice here that R0, well, let's look at C0 already. I discussed that. See, the speed of light has to be increasing. So C0 really isn't C0, it's C0e to the HOT. Okay? And R0, let's take a look at R0 now. What is R0? If we have a universe that's a sphere, R0 represents the diameter of that. Well, as time goes on, R0 is getting bigger, the universe is getting bigger and bigger. That's the whole point of this operation here. The universe is getting bigger and bigger. R0, therefore, is increasing, and it's radial, so it has the radial expansion factor of H0T. Okay? Now, what does this say? T0 is equal to the ratio of those two. Notice they cancel out, and so T0 is unchanging. It's equal to R0 over C0. That's T0 is a constant. That's a constant because the two expansions cancel out. That's the whole factor, by the way. Okay? Well, what does that say, too? 1 over T0 is equal to C0 over R0, which is a constant. And 1 over T0 is HO, and this is Hubble's constant. So what really is going on here is that these galaxies are moving at the speed of light for their particular position dictated by the time from some R0, from some initial point. And I will throw that in. It takes quite a bit of thought, but I will show you that also. But what we have here are some relationships. HORO is C0. C0 times T0 is equal to R0. All these things add up, and these are mostly, I think, Hubble's observations, but the only thing is that he did it considering a not
exponentially expanding universe. It's not exponentially expanding, even though his math says it. He didn't consider that, and of course, the standard model doesn't either. Now, if you remember, the Maclaurin expansion of this expression is that R is equal to R0, since this is a very small quantity, times HOT plus 1. That means you start at R0 and you add HO R0 times T. That's what the new R is. Well, this says R0 plus C0 times the T that it's moving. This is, final velocity is equal initial velocity, final position, final distance is equal to the initial distance plus the velocity times the time. So this is very consistent with the way things are. This and is the correspondence principle. If we see something going on the Earth, it should really break down that whatever model you have should tell you what the laws on the Earth are also. And that's what I'm claiming right here, that this is consistent with the laws on the surface of the Earth. One other thing I wanted to mention about what we just went over is this T0 is equal to R0 over C0. This is the age of the universe. If you look at this whole deal and you look at time in this model is contrary to time in special relativity and general relativity. Time is absolute. All we're saying here is that time changes the same everywhere in the universe. This takes you back to Newton. Time does not dilate according to this model. Not as far as I can see, and I'm pretty sure about it. Time is absolute. Now, understanding this, it's kind of easier to understand time changing everywhere at this same rate.